Thank you, Erik, for your nice introductions. And I would like also to thank Battery 2030 team, and especially Christina, and you, Erik, and Camilla for arranging this talk today. And so, as you mentioned, I am CNRS Director of Research at the University of Bordeaux, and especially at ICMCB. And I will give a talk on, I will try to highlight how solid-state chemistry can bring a lot in the innovation of metal-ion battery next generations. So first of all, I will give a few words on ICMCB, so our laboratories. So this institute is localized at the University of Bordeaux. And as you can see on this slide, we have three sites, the main site being this one. And we have expertise in solid-state chemistry, material science, chemistry and processes, and with the support now also more and more of artificial intelligence. And the director of this lab is Cyril Aymonier since 2022, and I am the deputy director of this lab. So in fact, for those who would not know, Bordeaux is localized here in France, and so this lab is there. And we are about 2,050 people in average, and belonging to these three institutions, CNRS, University of Bordeaux, and Bordeaux ENP. And as you can see, we have 110 permanent researchers, engineers, and technicians, and all these here are either PhDs, non-permanent postdocs, engineer or technicians, and at today, few masters, they will join the lab from January 2025 as each year. So our expertise are really based on the knowledge of condensed matter. Of course, I would say taking into account the resource, and all our expertise, solid-state chemistry, chemistry and processes, and material science are really dedicated to proposed new materials or to optimize materials in the field of energy, environment and health, electronics, and photonics, with the support of life cycle assessments and also artificial intelligence. So we have 7 research groups, as you can see here. I will not go into the detail of these 7 research groups. I just wanted to mention that our group is the group Energy, Materials, and Batteries. And since 2022, the Professor Darny Callier is leading this group with, as you can see here, about 45 people in this group at the present time. So what is interesting here for you, I think, is to know the keywords concerning our research. We are involved in batteries and supercapacitors chemistry, especially proposing positive electrode materials and solid electrolytes. And our expertise is really the crystallochemistry, but also, I would say, from the synthesis of the materials to the behavior in the battery or in the supercaps. So we are really focused on the characterization of the mechanism. We want really to address the role of defects and to then do also the link with the chemical bonds and the electronic structures in these materials. Combining our expertise in diffractions, spectroscopy, microscopy, and theoretical calculations. So the first part of my talk will be dedicated to highlight how solid-state chemistry can still bring new results on high-voltage spinel, LNMO, as positive electrode material for the next generation of battery. Like this, I wanted to highlight how our expertise can really bring some new knowledge in that field. And I wanted also, of course, also today to focus on especially raw materials and the need to develop materials that take into account, I would say, this constraint. So first of all, as you know, metal-ion battery chemistry is in fact a series of challenges because we have the material that the crystallochemist develops that will be involved in an electrodes with carbon additive binders on the current collectors, but then this one will be integrated in a battery, and this battery will deliver a capacity over a number of cycles. So it can be, of course, the autonomy for a car, for instance, but depending on the use of this battery, of course, we will have more or less fast aging, depending on the temperature, depending on the C rate of charge, and so on. So we have a lot of reactions that can occur in a battery, as illustrated here. I will not go into detail, but what we have to retain is a battery is a metastable systems, and I would say the material by itself, so here the positive electrodes, but also with these interactions with the electrolyte himself being also metastables. So we have really to understand all the reactions involving the materials, its interfaces, and I would say even the cross-talkings with the other electrodes in order to optimize a chemistry of a battery. So, of course, in our group, we developed material research in order to try to respond to these challenges and, for instance, to propose new material for high energy densities, for fast charging, safeties, and taking also into account the raw materials availability. And so, as mentioned, I will focus today mainly on that point, mentioning some materials for lithium-ion batteries, but also some new technologies such as sodium-ion batteries. So, of course, a battery is made of two electrodes and electrolyte, and you have different scale you can look at. Here, I would say the electrode, here the materials, and in our case we are more focused, I would say today, to this scale here, the crystal structures and the atomic and electronic structures of the materials, of course in interactions in the electrodes with the electrolytes. So here it's a kind of recap for lithium-ion batteries of generation of positive electrode materials we have worked on. You can see here that we do not have so much structures still in developed in batteries. We are moving here from layered oxides to olivine, so has LFP here and LFMP, then to spinel, and then again to layered oxides with lithium in excess in these materials. We can see that you have different chemistries here along this arrow here, and at first the motivation was really to go towards, I would say, longer life, more safety for all these materials here, moving from lithium cobalt oxide to NCA, nickel cobalt aluminum, and NMC, nickel manganese cobalts. And in that case, we were really playing with the cationic redox. Now, in order to answer to more and more demanding applications in energy, we are also moving to other chemistry, such as lithium-rich layered oxides, rock salt type structures, and high voltage spinel. And in that case here, for the lithium-rich and layered oxides, we are even jumping in structures, compositions, where we have cationic redox and, in addition, anionic redox. At the present time, we are all highly interested by these materials due to the fact that all these materials answer to another constraints when we develop materials. It's a resource. And here you can see that all of them are rich in manganese. Lithium iron manganese phosphate, the high voltage spinel that is rich in manganese and nickel, and all these lithium-rich are also rich in manganese. So today, in fact, I will highlight our expertise and new results we obtain on these LNMO materials, so these manganese-rich materials. And then I will move to sodium-ion technology. So first, the general context concerning these materials. These materials is often presented as with this composition here: lithium nickel 2 plus 0.5, manganese 4 plus 1.5, 0.4. And we are in fact expected for these materials the only involvement of the nickel 2 plus as a redox couples in these materials. You can see here nickel 2 plus, nickel 3, nickel 4. And you can see first that if we compare here the electrochemical curve of these materials here in black versus a conventional NMC here in red, we can see that with these LNMO materials, in considering the energy density, we can really compete. We have, considering the materials, 650 watt per kilo versus 700 for the NMC chemistry. But I would say the great interest for these materials is really the fact that it's a manganese-rich materials, and it's also a lithium-poor material. You can see that here, on the contrary to NMC, we have a lithium over transition metal ratio that is 0.5 versus 1 for NMC, and we have a nickel over transition metal that is smaller than 25% and manganese rich versus often more than 60% in an NMC. So in fact, if we consider the metals, you can see here that we have a decrease in lithium content of 50% for this chemistry. Of course, no cobalt, a decrease of 60% in nickels, and of course an increase to compensate in manganese. So of course this materials is highly attractive. So then if we come to I would say the structure of these materials is based on a cubic structures, the spinel type structures, and we have in fact two structures for these materials. We have disordered structures, so it means that here on the octahedral side of these spinel structures, we will have manganese and nickel that will be statistically distributed, whereas lithium will sit on tetrahedral sides. So this polymorph is obtained at a higher temperature than 900 degrees when we do the synthesis at these temperatures. But in fact, here I use this tilt here because in fact, when we are doing these temperatures at high temperature, we have always a tendency to lose oxygens, and so not to have exactly this formula, but to have oxygen loss, reorganization of the material with generation of impurity, and then for charge compensation, reduction of manganese. We'll come back to that later. And we have a second structure for these LNMO that is also cubic. And when we reanneal these materials at lower temperatures, 700, we have a rearrangement of the transition metals, I would say, within the samples. And in that case, the pure phase can be obtained with unordered structures with nickel in octahedral sites, only nickel 2 plus in that site 4B, and then manganese in the other sites, 12D octahedrals also. So in fact, I would say the phase equilibrium when we are doing the synthesis of the spinel oxides is really can be really described by these equations here. We are really always in balance between an ideal stoichiometric phase with only nickel 2 plus and manganese 4 plus, and with a deficient phase in manganese that does contain manganese 3 plus for charge compensation, and impurities rich in nickel in that case. with, of course, an evolution of oxygen. And then when the other question here is when we speak about order and disordered structure here, the question is also, and it was addressed by our colleague Montse Cabanas and co-authors in 2016, the fact that, in fact, we are not really able to describe exactly how is organized this order and disorder at the particle level and even at the powder level. You see here, if we are in the 1,1 plane in these materials, so disorder is described here with this statistical distribution on the 16D sides of the nickel and manganese. When we move here to the ordered, we have this again, this 4B and this 12D. But in fact, in the material, we don't know if it is a coexistence like this of ordered domain, more or less big, I would say, and next to them, disordered domain, or if it is much more subtle than that, with antiphase boundary, as you can see here, or only anti-size defects, and I would say in that case, in the ordered phases, and in that case, I would say kind of punctual defects. So in order to have more information on that kind of disordered, ordered model, we need for spatial information, and I will give you some clue about that in my talk. So then, another information that is very important here is also with the ordered LNMO, you have perfectly ordered, you have this green signature here. And so as you can see, only the involvement of the nickel in the reactions. Whereas when we move to disordered phases here, we have here the involvement of the redox composed manganese 3, manganese 4, in addition then at higher voltage to, again, the nickel redox. But here also still debates. In the literature, we can find different, I would say, statements about what is better, to have an order, to have a disordered phase. So the ordered, of course, is only a manganese 4 plus phase, when it is a perfectly ordered materials. And in that case, it is associated with higher structural stability, because when we have manganese 3 plus, we have always problems with manganese 3 plus dissolution upon cycling, and the involvement of these manganese in the redox processes. On the other side, disordered is often presented as having higher capacity retentions, higher C-rate abilities due to this mixed valence we have here between manganese 3 plus and manganese 4 plus. So still a lot of debates, and often the phase nickel 0.4, manganese 1.6 is presented as the best one, I would say. So as mentioned, still a complex system, considering especially that all these are highly correlated. The oxygen loss we have during the thermal treatment will control the nickel over manganese stoichiometry in the active phase, considering that, of course, the stoichiometry in the compound in the nickel over manganese does not change. But depending on if we have impurity or not, next to the active phase, we can have a very different stoichiometry in the active phase and very different impurity next to it. And depending also on the stoichiometry, we have, as just mentioned, the presence of manganese 3 plus. I mentioned also the importance of this materials. This materials is a high voltage material, so it means that we are here doing the reaction, the redox reaction at 4.8 volts. So in a domain, voltage domain, where the electrolyte is rather unstable, mostly the electrolyte. So today I will not mention, but in fact, in the literature and in our labs, we have a lot of research also in order to improve and to modify this electrolyte with additives in order to stabilize the interfaces of this material with the electrolyte and the stability of the materials. Because you can see here that as soon as your electrolytes, your salts here is degraded, we form some HF And of course, here we can have an acid digestion of our materials at the surface, and especially the solubility of manganese 2 plus generated by the dismutation between two manganese 3 plus, giving one manganese 2 plus and manganese 4 plus, and then migration of this one at the negative electrodes, and being the source of loss of performance for these materials. So of course, we want really to mitigate the amount of manganese 3 plus in these materials. I just wanted also to mention that, of course, coating can be a part of the solutions also in order to stabilize these interfaces. Sorry. So today, in fact, I will mention results especially obtained in the thesis of Ilya Tertov that was funded by the European program InnovaXN and ILL, and Ilya will defend next Monday, and also a short view about work done by Gauzeoni, who developed food stem analysis in order to get spatial resolutions of these materials. It was done in the frame of an INR programs. So the question was, is disordered LNMO always the one that performs better? Cannot we have some ordered LNMOs that performs rather well and competitive with these disorders, and so close to the perfect stoichiometry? How are distributed ordered and disordered domain, and which perspective we can give to this work? So in order to try to answer to these questions, we collaborate with Umicore in the frame also of this work, and with LRCS. And in fact, we did large batches of materials, 18 samples that were performed by Ilya in Umicore, and starting with hydroxide metals precursor from Umicore, you can see here. And in fact, in these synthesis conditions here, at very high temperature for the first thermal treatment, in order to really to promote growth of the particles, and so to promote low specific surface area, and thus I would say less interactions with the electrolyte and more stability versus degradations. And then we did a lower thermal treatment in order to try to promote the formation of the ordered phase, and that we did. And here, just to highlight, 75-25 corresponds in fact to the composition of manganese and nickel. So here we are in the stoichiometric conditions, air in the atmosphere. And so we have really varying the manganese over nickel ratio, deficiency in manganese, stoichiometry, excess in manganese. We have varied the composition in lithium, deficiency in lithium, stoichiometry, excess of lithium, and we have used different air versus oxygen. So I will not give you all the detail of the results obtained. I will just focus on a few results in order to highlight the main results. So first of all, I would say the originality of this work is also that we combine synchrotron X-ray and neutron diffractions in order to really take the advantage of both techniques. And here I took four samples in order to highlight this. So 75-25 here under air or oxygen in red, so are the stoichiometric materials, and 77-23 in air or under oxygen are the manganese excess materials. So when we use synchrotron X-ray, of course, we can distinguish lithium versus transition metal ions, but we cannot distinguish nickel and manganese. And you can see also that using synchrotrons, we are really able to detect very tiny peak. So here in blue, it highlights peak associated to rock salt type impurity, nickel rich. But you can see that it highlights also already by X-ray peak 3 2O associated to an ordering between nickel and manganese. And so it already highlights that we have an ordering between nickel and manganese in at least these materials here that were obtained under oxygen. So now if we jump to neutrons, the benefit of neutrons is also really that we can distinguish nickel and manganese in these materials. And so we are able to distinguish what I have called at the beginning the disordered structures with a statistical occupancy of the octahedral site and the ordered with one site for one transition metals. You can see here in red, in gray, I would say the older superstructure line. And you can see that for all of them, we can see the superstructure line. Whatever the synthesis conditions, I recall you that the second thermal treatment was done at 725 degrees, so in the domain of stability of the ordered phases. But it is also interesting to highlight that depending on the conditions, you can see that the superstructure line associated to this ordering between nickel and manganese are very different broadenings, moving from, I would say, sharp line to much broader line, and even here much more diffuse. And that, you will see, it will be associated to the size of the ordered domain. So here, I just wanted to highlight the fact that here it's really a dome of a synchrotrons X-ray diffraction pattern that we were really able to identify the impurity, at least from a structural point of view, and to identify the presence of rock salt impurity as often observed in that kind of materials, but also of different layered oxides impurity. You can see here different peak associated here in the backgrounds. So here, this graph here give an evolutions according to the composition in manganese and nickels here, the stoichiometric here, deficiency in manganese, excess in manganese, and here at the bottom you have the stoichiometry in lithium versus transition metals. You can see that for this, so the more green it is, the purer is the LNMO phase, as you can see here. Here we are close to the purity, and we are here under here. With oxygen here, we have a full purity of these materials here. So you can see that depending on the conditions, we can really have highly impure materials, such as this one, with different nature of impurity, as you can see here, spinel, rock salt. And for this one here, for instance, we have layered and rock salts. So for this one here, the blue one, so the manganese excess, stoichiometric in lithium, we have the presence of a tiny amount of rock salt impurity. So you can see that we have 3 types of impurity in that kind of materials. So then it is also interesting to do the link, of course, with the electrochemical performance. And we have tested that material either in C-rate conditions or in long cycling protocols. I have to add versus lithium in that case. So here you have, I would say, low C rates, D over 10, fast C rate, so 20-minute charge, and here you have the Coulombic efficiency. And again, the y-axis is still the same, the manganese nickel compositions. Here the x-axis is still the lithium over metal ratio, and here you have still the green, of course, is the better. And you can see that the better performance are obtained for manganese excess compositions, so 77 over 23. If we look more carefully at the electrochemical curve, so here you have the air materials, oxygen materials, and here the stoichiometric, and here the excess of manganese. You can see that we have slight modification of the electrochemical signature. You can see that for this one, stoichiometric composition under oxygen, we are really able to have almost a pure stoichiometric materials and ordered signature with this derivative here, despite a small amount here of manganese 3+, as you can see here by this signature here and by this jump here. And here, for these other composition, you can see that we have much more complicated evolutions here with two peaks here in the derivative curve that can be observed for this one obtained for manganese-rich materials. And this was associated to the presence of manganese 3+ in the materials, but on the two sides, 4B and 12D, and so with the redox activity of one manganese 3+ in one side versus the other activity at a higher voltage in the other side. Interestingly also, you can see that at C rates, we have some materials that behave much better than the others, and especially here you can retain the colors orange and green and light green, strong green, that behave much more better upon long-range cycling, but also together when we consider C-rate behaviors. And so it's of course very interesting to go deeper in the understanding of the structure of these materials. And it's also interesting to highlight here that you have much worse behavior for the fully stoichiometric materials obtained under oxygens that shows no impurity in that case. So if we go further in the structure of these materials, I just put these materials in order to this X-ray diffraction pattern just to convince you that the results were, I would say, of good quality, but we will focus really here on these results here. So if we consider the manganese-rich material, whatever the atmosphere we are using to prepare these materials, in fact, it does not change so much versus the structure. You can see that the cell parameters are very similar, and I would say the distribution among the two different sites also. We have manganese, a manganese site that is full of manganese, and we have a mixing in the nickel site between manganese and nickels, and of course manganese 3+ and nickel 2+. But you can see that depending on the atmosphere, in the similar annealing condition, we can have a difference in the size of the ordered domain that I had associated to the superstructural line broadening here. Now, if we move to these stoichiometric materials here in orange and red, you can see that for the red one, stoichiometric under oxygen, we are almost at the perfect distribution between the two sites. And we have also big size for the ordered domain. And again, under here, much smaller domain size and similar distribution and mixing versus with manganese-rich materials. So in fact, this combination of X-ray synchrotron diffraction and neutron diffraction allows us to really describe these materials. In fact, all of them have to be described in the ordered space group P4332, and known in the disordered space group FD-3m, with more or less extended size of the ordered domains. And then we have shown also that we have a manganese partial occupancy on the nickel 4B side. You can see it can vary from 2% to 5% for that kind of materials. And then we have also different size of ordered domains. So now, so that it was for given synthesis compositions, playing, I would say, with the compositions of the materials. But now what happens if we take these manganese-rich materials obtained under air, and if we do the thermal treatment at different temperatures, here moving from 625 degrees to 725 degrees, how these parameters evolve? Do we have always the same tendencies? And in fact, I will not show here the performance, electrochemical performance, but in fact, we have really the same tendencies. Look here in blue. In blue, we have the manganese-rich materials versus the red here, the stoichiometric composition materials. In fact, you can see that in these materials, we have bigger order domains obtained here when we are manganese-rich versus for the same temperatures, smaller domain when we are at the stoichiometric compositions. And you can see also that we have a higher mixing when we are we have a higher mixing here between the nickel and the manganese side. These parameter here being a kind of scale for the amount of mixing between the two sides. When it is no mixing, this parameter is 1, and with the increase of the mixing, we are moving towards 0.5. So you can see that we have more defects for these manganese-rich materials, despite, I would say, the bigger order domain. So, of course, it's interesting to determine how are organized these domains. And for that, we did some microscopy because, as you have seen, really these materials are those who behave the better in the battery. So, of course, it's interesting to understand how organized this order domain and to propose an hypothesis why it happens like this as better electrochemistry. So as mentioned just before, these crystallographic planes allow really to see, I would say, the arrangement between the nickel and the manganese, and thus to have an highlight about the extent of the ordering or defects in these materials. And so this work was performed in collaboration with IMAT in Antwerp and Umicore and Dimitri and Mylène, and they did this cutting here, feed cuttings along these directions here in our particles in order to have thin layers, thick 50 to 100 nanometers, and to be able really to have an information from the surface of the particles from here to the bulk of the materials. And they did some different analysis of the images they got by microscopy, combining different Fourier transform, masking, and so on. And they were really able to show that we had in our materials some, as you can see here, area where, as shown here by the electron diffraction pattern, that we are here in a disordered area. So it means indexed by the FD-3M space group. And here we are more in ordered, where we have these additional spots here showing that we are in this P4332 space group. So what does it mean if we go further? In fact, if we look to these images here, we have from the surface to the bulk of our materials, a mosaic organizations in the thickness of the particles in the bulk. And you can see that when we, I would say, screen the particles, we have whatever from the surface to the bulk, the same size, average, equivalent diameter for this domain here. All these gray-white are associated to ordered domain. And what is very interesting much more is, on the contrary to what we have thought, we could have expected a core shell effect due to this oxygen loss during the synthesis. We have in fact a mosaic effect with ordered domain here and disordered here at the boundaries. And I spoke about this effect of temperatures. When the annealing is performed at 625 degrees and moving to 700 degrees, you can see that we have exactly the same mosaic effect, whatever the temperatures. And you can see that we increase the size of these ordered domains from roughly 10 nanometers to 30 nanometers here. And if you remember, we had for these materials also performed neutron diffraction experiments in order that allows us to evaluate the size of this domain. And for these 4 materials, we have a very good agreement between TEM and NPD. So I wanted also to highlight that you could say these materials were obtained 1000 degrees first and then low temperatures in given conditions. It's perhaps specific. Yes, it's also this technique that is used by microscopy. So here I wanted to highlight another result that we obtained also very recently in collaboration with LRCS, Arnaud de Mortière. And these platelet particles here, LNMO, were obtained in different conditions in molten salts in order as thin platelet in order to be able to use the photostem analysis and to do cartography on the platelets in order also to be able to localize ordered and disordered domains. And you can see for these particles here, we have a link to this material here, very close to the stoichiometry, and as shown here also in blue by this lithium mass NMR spectra, we have a single signature for lithium in this material in good agreement with the almost perfect stoichiometric materials. And here, for the spinel that shows already defects, ideal for disordered, manganese-rich, we have a much more heterogeneity in this particle with here a disordered domain and here ordered domain. So just to conclude this part 2, I wanted to say that in this material, we are not in disordered materials, and they behave very well in a battery in electrochemistry upon long-run cycling at high C rates. But we are in material where we have this mosaic effect of ordered domains. And as you can see, percolated by disordered small domains. And we think that both contain, in fact, manganese 3+, and that it's source of mixed valence. And it's, in fact, the key for optimized electrochemical properties. Of course, we still have manganese 3+ in these materials, but you can see a very small amount of manganese 3+ versus composition of unreported in literature. We have also small specific surface area versus the electrolytes. So, of course, the next step for this study is really to test this material in full cell at 55 degrees in order to check for the stabilities. And I wanted also to highlight after this first part that here I have also illustrated the necessity for implementing spatial resolve techniques such as photostem in order to come to these answers here. So then I will move to the sodium-ion batteries technology. And I wanted to say that, in fact, the motivation for the development of this sodium-ion battery technology, of course, is the localization of the resource, I would say not equally in the world, and especially more in America, in China, and in Australia. And you can see it is, in fact, produced in a very limited number of countries, with 95% of the production controlled by a few number of countries. And you can see also that we have, as we know, a lot of pressure sometimes on these lithium carbonate and nickels. So in fact, as you know, in our lab, and others. We are a lot working now on sodium-ion battery technologies that can be really an alternative sister technology for lithium ions, despite intrinsically a smaller energy density, but it is also attractive due to the fact that, in fact, here we are with the raw material abundance. You can see that here. So the more it is orange, the more abundant it is. If we compare sodium to lithium, it's much more abundant. If I remember, 3 orders of magnitudes. And the other good point is also that sodium does not form any alloy with copper. So we can really use also aluminum at the negative electrode. So it means that we replace copper that is less abundant by aluminum that is more abundant. And of course, we have also sodium in Earth's crust, but also, of course, in seawater. So in fact, this technology is based on much more abundant materials. Of course, it's a complex system. I will not go into detail in this technology. We have at the present time 3 main chemistry developed at the positive electrodes. We have also a lot of works that are done on these hard carbon in order to study the best structure for these graphitized nanodomain for hard carbon. And also a lot of works, I would say, especially to do also on the electrolyte due to the key role of these electrolyte for the behavior of these sodium-ion batteries. And so again, a lot of research were done on these materials in order to develop new materials at the positive electrodes. You can see it's also interesting to highlight that, in fact, here you have the energy density, the specific energy, and here you have different chemistry. Here at the top, you have the lithium-ion batteries, and here I would say the sodium-ion batteries. You can see that versus hard carbon here or versus different negative electrode. You can see that for some of this chemistry, we can really compete with, for instance, the LFP or the LMO versus graphite lithium-ion batteries as alternative. So the growing activity around sodium-ion batteries, I would say even at the industrial levels. And today I will give a few information about these materials and about new chemistry that we prospect beyond, I would say, these materials. I will not go into detail also. This just to show you how we bring this material from the lab to the introduction in a battery that is now developed by Tiamat. And so this material is very interesting. It's a 3D materials. You have here this bioctidal unit, and you have here along this bioctidal unit fluorine, and here in the square here of these octahedra oxygen. And we can play, in fact, with the oxygen fluorine stoichiometry in these materials. You can see that other chemistry are developed, layered by and Prussian blue. So here I wanted also to highlight that here also the solid state chemists play a big role in the development of these materials because you can see that in the literature we had all that kind of electrochemical signature, and I would say even more this kind of electrochemical signature for the material I will call NVPF in the following. You can see that in fact, here we have very different content in oxygen and fluorine in these materials, and that this signature is really the one of NH3V2PO42 times F3, so only fluorine here. And what happens when we have this electrochemical signature here? In fact, we are moving from this bioctidal unit, vanadium 3+ rich, fluorine along the direction of the bioctidal unit, and we increase here the oxygen. We have oxygen defects in these materials, and we do not control the fluorine stoichiometry. And in fact, we are oxidizing vanadium 3 to vanadium 4, and in fact, creating these vanadium-type bonds here. And here I wanted also to highlight that in order to really detect these defects and to be sure of the stoichiometry in oxygen and fluorine here, the probe phosphorus solid state NMR is a really good probe. You can see that when you increase the oxygen in these materials, you have more and more NMR signals, in good agreement with the fact that when you do not have oxygen, your phosphorus here is only surrounded by vanadium 3+ octahedra. And the more you have oxygen, you increase the number of vanadium 4+ octahedra around it, and you change the transfer, the electronic transfer from the vanadium to the phosphorus. And so it means this shift from high shift in NMR to diamagnetic shift in NMR. And I wanted also to highlight that these techniques also here allows to really detect very small defects in these materials here. You can see here. So already at that time, in collaboration with the frame of the ALISTORE network, we were able, here in full cells versus at carbon, with collaboration with the group of Maria Palacin and Patrick Johansson, to demonstrate that this material was very good at high rate. You can see here in lab prototype, we had almost no loss of capacity moving from slow rate to high rate here. And I would say that we were able already at that time to improve the performance, changing the chemistry of the electrolytes. So then we merge effort with CLE10 in order to do the upscale of these materials, and especially to be able to promote the formation of these materials with a controlled carbon coating at the surface. The homogeneous coating is the key of the function of the performance of these materials. Of course, it brings the conductivity within the material, within the electrode, but it brings also the stability of the CEI, and especially also versus vanadium dissolution. And we were able to upscale these materials. And also, we have shown that playing with the synthesis, we can really play with the microstructure of these materials, moving from nanosphere here to platelets and to rock, sand roses here. And depending on the microstructure, we can also play on the electrochemical performance. And we have shown very recently that by mechanical grinding, we can really increase the tap density of this material also, with, I would say, maintain performance in that case. So prototype were performed, first prototype were performed by CA in order to demonstrate the interest of the technology. And you can see that it is interesting here when we are in a prototype for power prototype here. You can see in blue that we can really discharge the battery at very high rates, and charge here also in 6 minutes the battery. And we had demonstrated also at that time a very long cycling for these materials, so stability upon cycling. So just a few slides on this technology that I obtained with the courtesy of Tiamat. So for this technology, you can really do a fast charging, high power density, and superior safety of these materials. We can really store the battery at 0 volt without damaging the performance, and no fire, no thermal runaway, long lifetime, and based on abundant materials. So here it was a work performed, I would say, from a material proposed first by the solid state chemist, bring to maturation, and now integrated in a technology that is developed by an industrial. So I will finish by highlighting 2 recent results obtained in our group. One on manganese substituted NVPF, and one on new nascent materials. So in order to show you that Solid-state chemists are also, I would say, force of proposition for new materials, again for the sodium-ion technology. So in fact, Gaël Minard, funded by the INA programs, developed during his PhD the new materials. So same structure as NVPF, and in fact the same materials. But as you know, we really want to promote to maintain the structure, but with more abundant materials. And he was able, through these topochemical reactions we had used a few years ago, to synthesize these materials, NVPF, oxyfluorine. In fact, by topochemical reactions here, these are using this precursor, vanadium-rich, in ionic liquid media as source of fluorine, and also as media where we can do an hydrothermal, a solvothermal reaction at low temperatures, in order to really use these topochemical reactions with an exchange between with integration of sodium and fluorine in the structures, and vanadium reductions and formation of these NVPF materials. So we were only able to substitute manganese in these structures with exactly the same approach. It means to prepare this precursor here, and we were able to substitute up to 25% of manganese for vanadium in these structures. So in fact, we were also able to develop a new series of materials with a variation of composition in manganese and vanadiums, but also in fluorine and oxygens, and also in sodiums, as you can see here with the lattice parameters versus the composition in sodium in this material. You can see here a series of materials. And interestingly, these materials here behave very well. You can see we have very small polarization, very good reversibility of these materials. We have activity of vanadium and manganese in these materials, so it means no loss of capacity versus the vanadium-only materials. Very good behavior at high C rates and upon long-run cycling. Of course, it's preliminary tests in half cells, so these could be interesting to continue for better maturations. So then I wanted also to highlight these results concerning these new nascent materials that we recently published. So this work was performed by Situ, Park in Tiamat, and I would say starting from very old materials. You know, these nascent materials, Na3 with V2PO4 3 times. In that materials, you have vanadium 3 plus materials. And this reaction this material behaved very well. We have a flat plateau. We have the exchange of 2 sodium per formula unit and 1 electron per vanadium. So vanadium 3, vanadium 4. And you can see that we have very good performance at high rates. So already demonstrated. But in fact, a colleague did, Piero Canepa did calculation on this material, and he said, he told us, here I think we have an intermediate phase, and in fact, Na3, Na1 is not a B-phase reactions, but 2 successive B-phase reactions. So of course, we were interested in order to prospect these reactions. And first we prospect literature, and we saw that we had some already intermediate phases in some results reported by other colleagues, but not mentioned and not analyzed. And in fact, we did these experiments at synchrotrons ALBA. And as you can see here, when we move from Na3 to Na1, we have Na2 intermediate phase, Na2, that is observed when we are in non-equilibrium conditions. And you can see also that we do not have a symmetric behavior between charge and discharge. And this Na2 phase could be isolated in synchrotrons, but could not be isolated when we recover the material from the battery. It's a metastable structure, and despite of that, of course, this structure could be determined. Of course, we were interested to stabilize and to search more around these materials Na2V2PO4 times. It's interesting because here we have a mixed valence for vanadium 3, vanadium 4, and we have only 2 sodium per formula unit, so I would say efficient sodium. And in fact, we did this chemistry here, mixtures between Na3 and Na1, and we did it in temperatures, in synchrotrons, and you can see that we move from 2 phases here to a single phase, but when we cool down, on the contrary to what we had in the battery, we have and we maintain a single phase that is stable at room temperatures. And we did this for different compositions and mixtures between Na3 and Na1, and we were able to stabilize like this a series of materials. Why these materials are interesting? In fact, they are interesting because on the left, you can see here the conventional electrochemical signature of NVP, Na3V2PO4 times, a flat plateau at 3.45 volts, and you can see here the signature of the new nascent material Na2V2PO4 times. A much higher working voltage at 3.7 volt. It means plus 10% in energy density. We have solid solutions versus a plateau. We have much less volume expansion upon cycling, 6 versus 8%. And we are able to play between Na2 and Na0 that was obtained for the first time. And as I mentioned, we can even have a full new families of materials of NaXV2PO4 times, X varying between 1.5 and 2.5, with very different electrochemical signature depending on the content initially in the structure. Of course, the Na2 is the most interesting. So then I wanted to conclude this part by highlighting that it's only the characterization in depth of the materials, I would say from the local to the long-run structures and knowledge of defects that allows you to understand the materials. We have also a lot of non-equilibrium phase and mechanisms that are observed. And so for that, we need the development of in situ cells. And we are really still able to identify original mechanisms, new families of materials of interest for sodium-ion batteries. And I will conclude my talk by giving two perspectives to say that very recently, we have studied all these mixed anion chemistry here with phosphates, tavorite structures, as you can see here for lithiums, NVPF structure for sodium, and KTP type structure for potassium ion batteries. So this chemistry, not only the cation chemistry, but also the anion chemistry, is really a source of new materials for batteries, because depending on the composition in an ion, you can really play on the voltage and on the electrochemical curve, I would say the signature, and you can play on the potential of your batteries, here lithium, sodium, or potassium. And I will finish this really by mentioning also that it's worth, of course, to consider, I would say, much more abundant materials, such as iron polyanionic materials. And especially here, I focus on sulfate and sulfate phosphate materials. We found new phases recently. And of course, the challenge here is really to stabilize these materials and to optimize these materials in order to have very good performances. But they are very interesting because here we have in sodium, iron, and sulfur or phosphate systems, so only abundant element. And I will thank you for your attention, and thanks all my colleagues from ICMCB, Danny, Jacob, Emmanuel, and François, from LRCS, Christian, Jean-Noël, and Arnaud, and from the large-scale facilities, Antonella, François, Lorenzo, and Emmanuel. And of course, I would say all my best acknowledgements to Ilya, Gosdes, and Gael, Romain, and Anastasia. You saw either more longer or briefly their results, and you for your attention and all the funding.
Thank you very much. Yeah, thank you very much.